our speaker is Tandy Warnow, and she will talk a little bit about simulation study comparing phylogenetic reconstruction methods for linguistics.
Thank you. So this is a report about a project that's been going on essentially for the last approximately 13 years or so since I started at Penn, culminating with some simulation studies, but also some model along the way, and connections to phylogenetic networks for those of you who have been working on networks. And so this is a possible Indo-European tree. So what that means is it's a possible history of the Indo-European languages, with the first child being Anatolian, the second being Tocharian, then a group containing Italic and Celtic and so forth. And so, you know, we're used to talking about biological evolution, but languages also evolve, and languages also in some sense speciate. And they're the same issues about linguistic phylogeny as there are about biological phylogenies, namely the interaction between population level processes and species level processes, and the definition of what is a species, and for that matter, what is a language, what is a dialect. A lot of the same controversies that you find in biology apply here. So this is a phylogeny that we came up with quite a long time ago and published in 2000. And then subsequently, in 2005, we published a modification to this phylogeny where the red edges indicate burrowing. And what they actually indicate is undetected burrowing, because in fact there were obvious burrowings between lineages that are not written in there. Those red edges were burrowings that had not been previously detected using classical techniques of linguistics. So this is what one might call an explicit phylogenetic network. So it's actually not an implicit one, but an explicit one. It's saying that every character is evolving down this network by traversing either the underlying quote-unquote genetic tree, that's what it's called, or using some of the borrowing edges. So for example, you might have some trait that starts here and travels down here and then like this, and then it's borrowed over here, replacing the whatever was present in the ancestor of Italic, and then continuing down, okay? So these borrowing edges, the contact edges, represent times at which the speech communities are in communication with each other, in contact with each other, sufficient to allow for exchange of linguistic material in such a way as to not be obviously borrowed. So there's a lot that is actually obviously borrowed in languages. For example, the word, you know, I hate to call it the word television. I don't know how to speak Japanese, but evidently there's a word in Japanese that is the Japanese version of the word television. And it's very clear that that word is borrowed, right? Less obvious are words like skirt and skunk, which were all borrowed. They're not inherited genetically, they're borrowed. So there's a lot of borrowings that occur, a lot of which can be detected, but this is for undetected borrowing. Okay, so what you might notice here is a lot like coming up with a phylogeny of bacteria. There's the borrowing that's going on, but there's this underlying tree, and then the question is, how easy is it to get the tree? How much does the borrowing confound the problem? And that's one of the questions that we wanted to be able to ask. But I would say that even this underlying tree is controversial. Some parts of it are well established. Every single one of these leaves represents a family. So for example, Germanic is itself a family of languages. Baltic is a family of languages, and so forth. I suppose probably no one here speaks any Tocharian language, and probably no one here speaks any Anatolian language, but plenty of us probably speak some Italic languages. Okay? You won't find languages here like Hungarian or Dravidian, things like that. So this phylogeny, the components of it that are well established are each of the subgroups and Balto-Slavic and Indo-Iranian, but not Greek and Armenian as sisters, not the location of Germanic anywhere, not the location of Albanian anywhere, not Italic and Celtic as sisters. None of this is well established, and I would say that even we are not completely convinced about much of this, especially not the location of Albanian, which can pretty much float in a number of different places. And what's really controversial here are things like, where does Germanic fit in? That's one of the really controversial things. But just about everything about this is controversial, as is typical in any systematics endeavor. Okay. So controversies, other than the 10 major subgroups, what is the rest is likely to be true? In particular, is Italo-Celtic, that is the grouping of Italic and Celtic as sister taxa, is that reliable? Are Greek and Armenian sister taxa? Is there a split separating Anatolian and Tocharian from the rest of the language family? The Satem core are the 4 languages, Indo-Iranian and Balto-Slavic together. Is that a reliable clade? Where does Germanic fit in? What about dates? Can we estimate the dates for the ancestral nodes and use that to say something about human migrations? And finally, just how tree-like is Indo-European period? Because it's easy to see it's not perfectly tree-like. And there are some arguments that would say don't even bother to find anything close to a tree because it's really not anything like tree, it's really some kind of dialect continuum. And so by trying to do something like this, we're actually trying to postulate something in between a pure tree and a pure mess. So that's sort of the objective, is to see, can you come up with some kind of measure of deviation from a tree that you can then make an argument for? Okay. So there have been many reconstructions done on Indo-European, and a lot of controversy around it, and a lot of actually significant differences between the different phylogenies. And in particular, the location of Germanic is one of the things that people have really disagreed about. And some of the issues that might explain why we see these differences are they start with different data sets. They have used different kinds of data. They treat the data differently. They use different kinds of methods to do the reconstruction. There's all sorts of ways in which these methods have differed, both in their fundamental data and what they've done with the data. And so, trying to understand what's causing the differences is itself an interesting question. So we did a study that was published in the Transactions of the Philological Society, in which what we did is we looked at various different reconstruction methods, and we focused the attention just on the difference in the methods by keeping the underlying data set the same. And in particular, some of the problem that had been happening is that a lot of people's data sets have been based upon this Dayan data, which had a lot of problems. It was both very modern, so it had lost a lot of the features, and also had errors in it. So we had a very carefully curated data set that was put together by Don Ringe, my collaborator, and his postdoc, and had been very, very carefully done to be reliable about cognacy. And we used that data set, fixed that data set, but looked at various variations of that data set in terms of only lexical data versus all of the data, screening it versus not screening it. So 4 variations of the data set, and then we looked at the different methods on the same data sets. And that allowed us to look at the, yes?
What means being carefully put together? I assume these were all scholars who did their work also for the previous data sets, and they were all too careful.
No, actually, so there's 2 things. One is that the data set that Don Ringe put together had been circulated among the leading Indo-Europeanists. So it had been circulated to Jay Jasnoff and Craig Melchert and others, who had confirmed the judgments, and had, where there had been differences, they had been very few. And we also tested the methods on the small modifications to the data set. By comparison, the Dayan data had been very thoroughly criticized by leading Indo-Europeanists as having very obvious mistakes. So it really was a different quality data set. And that's, whether it's correct or not, the data set that Don Ringe and Ann Taylor put together had met with the approval of the Indo-European community at a much higher standard.
Careful selection of the joint prejudices of the experts.
Careful selection of the what?
Joint prejudices.
Well, one could say that. I don't think that I would say that because I'm not a linguist and I can't critique the judgments, but I would say since the other specialists agree with the cognacy judgments, and where they differ, it's not actually on the cognacy judgments, it's on the morphological characters interpretation, and even there the differences have not led to any differences in reconstruction. So I think in fact it's a very reliable data set. But again, reliable in terms of meeting the joint, how did you put it?
Prejudices.
Prejudices. Fine. Okay, so these are the data sets we looked at, and you can see there's actually 3 different kinds of characters. There's lexical, morphological, and phonological. So lexical characters are the standard type of characters that people work with, and there's way more of them than there are of any other type. Lexical characters are things like semantic slots for table. You take all the words in the different languages that had the fundamental meaning of table, and you say, are these words cognate? That means, do they come from a common ancestor via sound changes? There's also phonological characters, which are primarily binary, presence or absence of some strange innovation. So this is starting to sound like cladistics, a la, however long ago it was. And in fact, it's very similar. You look for very strange features that you think are unlikely to arise by chance. And if they, in fact, don't arise by chance, then they're better markers of evolution. But that, again, is a question about whether or not you picked them so as to meet with your assumptions of linguistic history, or if you really picked them because they're just strange physiological innovations. Certain things are obviously natural innovations. You don't want to use them, like the loss of an initial H turns out to be pretty natural. Then there's morphological, which are things like how you make words out of other words, how you make nouns out of verbs, things like that. So morphological features, phonological features, and lexical. And we looked at screened and unscreened. Now what screened and unscreened means is that the screened data set is everything. The unscreened data set is everything. The screened data set means you go through the data and you say, this is obviously borrowed, or this is obviously homoplastic, or this is obviously convergent evolution, in the sense of homoplastic meaning convergent evolution or back mutation. So you get rid of the characters that you are sure have fundamental problems with them. So you can argue that that also is potentially just confirming your biases, which is why we wanted to look at unscreened and screened both, okay? And then a lot of people have done all their phylogenies just on lexical data, so we wanted to look at lexical alone versus all of the data, okay?
And again, yes, what is obvious? Why is something obvious homoplastic?
Well, one could say that it's obvious that wings, the presence or absence of wings, is not a character that evolved without homoplasy in biology. And I think it's the same level of judgment that's applied. So there are certain things that are considered very obvious markers of problems and others which are not. And it's the same kind of issues, right? I mean, it's really the same kind of detail. So the 3 kinds of characters, lexical, phonological, morphological. Lexical characters are well understood to be the most easily borrowed. And it's natural that you would want to borrow lexical characters, because if you're in contact with a new community and you need to be able to communicate with them, you need to be able to use their words. Those are the things that happen. And then you end up, there's a lot of documentation about words that are borrowed. Phonological characters can also be borrowed. A sound change can go through a population and sweep through a neighboring population. But that happens with less frequency than lexical. And complex phonological characters, the kinds that we've primarily been using, these are not just presence or absence of a single innovation, but rather first this happens, then that happens, then that happens. Then there are things like Grimm's law. I'm not sure what Grimm's law is, but it's a sequence of these simple phonological characters that happen one after another, and they've been used to establish different subgroups within Indo-European. And finally, morphological characters are the least easily borrowed and the least likely to be homoplastic. But homoplasy does happen in all of these characters. And that's been one of the surprising things, is that for a long time we thought homoplasy just wouldn't happen if you did a careful analysis. But it does happen, and so you have to actually deal with it. So these are the languages that we looked at, and it's not really important to memorize what these things stand for. These are the methods that we analyzed. So we looked at neighbor joining, and we used neighbor joining on a distance matrix with distances corrected according to a model of linguistic evolution. We looked at UPGMA, which is just the standard look at the handling distances between the languages and just group them together for the 2 that are the closest together, have the smallest number of changes, and then recurse. Maximum parsimony in the same usual way, maximum compatibility. And now we looked at 2 different versions of maximum compatibility, which is weighted and unweighted. So maximum compatibility says you want the maximum number of characters to be compatible on your tree, which means they evolve without any homoplasy. weighting that means that you allow the linguist to specify some prior assumption about the resistance to homoplasy. So fixing that weighting and then looking at weighted compatibility. And we also looked at a method that Gray and Atkinson came up with, which is essentially running a Mr. Bayes binary character analysis on a binary encoding of the multi-state characters. So the binary encoding basically takes each multi-state character and encodes each multi-state character as a collection of binary characters, so presence or absence of each state, and then treats them as independent. So those are the methods that we looked at. And some of the observations are UPGMA actually did the worse, which is to say that it split known subgroups. I have to say, however, that because of how we picked our data did not all happen at the same time. They are not selected all to be modern data. We had the latest data we could pick, meaning the furthest back in time for each language family. So we had very ancient data for some groups and more modern data for others. And so it's not surprising that UPGMA would do the worst because you're not sampling all from the same time depth. But it did do the worst. All the other methods agreed on all the 10 major subgroups. In addition, they all came up with a split dividing Anatolian and Tocharian from the rest, and they all reconstructed Greek and Armenian together. So that's pretty interesting because these are not accepted analyses. To say that Greek and Armenian are sister taxa is not necessarily an accepted statement. It's still debated. To say that there is a split between Anatolian and Tocharian is not necessarily accepted. It was nice to see that the methods all agreed. Yes?
Did you try anything like split decomposition or naming it just to see whether that would?
No, we
produce
didn't.
anything?
The Saturn core, which is Indo-Iranian and Balto-Slavic, is not always reconstructed. Sometimes it is, sometimes it isn't. And almost every analysis put Germanic with Italic and Celtic. And the only methods that did not put Germanic with Italic and Celtic are the ones that the ones that used weighted maximum compatibility and weighted the morphological characters very heavily and included morphological characters. And otherwise, all of them put that grouping together. So this seems to be an aspect of the evolution that is only reconstructed under some conditions using some data with some methods. Yes?
I don't remember anymore. Is it Kurdish?
Kurdish? No.
No, because it's Indo-Germanic and would be interesting with all the other languages where it would go.
Yeah, it would be.
But we have
Where do you think it goes? Just curious, where do you
it's
think
clear.
it goes?
It must somewhere be close between Iranian and Turk and Indian whatsoever, but nobody knows.
Okay, well,
I mean, for a long time I didn't even know that it's Indo-Germanic, but it is Indo-Germanic.
well, I will ask Don if we can look at it. That would be fun. Okay, so here's an example of some of the trees. It's not really important to look at this very carefully, but just to see, this is on the screened full data set. So this is where we've gotten rid of all these suspicious characters, okay? But we're using all the different characters together. And we don't show maximum parsimony here because it's really the same as maximum compatibility. But what you can see here, for example, here's Latin, here's Oscan and Umbrian. These should actually be together. So this is the UPGMA tree. It's actually splitting the italic group. Neighbor joining has, here's Italic and Celtic and Germanic. And you see the same thing here. You don't see it here. So this is an example where here's Germanic here, and here's Italic, but Germanic is not grouped with Italic and Celtic. So it's just some of the places where you see some differences. And the location of Albanian is really not important. It just floats. It's because it's lost most of its morphology. So the different methods give different answers, and we really don't know which method is giving the right answer. We don't know if any of them are giving the right answer. We don't know what answer is correct. And so we don't really know what method to use. We don't know what data to use, right? I mean, it's the usual thing. You have a real data set, you have different analyses, you don't know what's right. So, you know, in biology, the use of simulations has really had a huge impact on understanding methods. And we wanted to bring that into the linguistic context. Now, we were not the first ones to bring it into the linguistic context. But I'm going to just tell you about what we did in terms of a simulation. So, you know, the usual simulation, you have some true tree, you generate, in this case, DNA sequences, you reconstruct a tree, and then you measure the error in the reconstructed tree. So for those of you who have seen this before, this is kind of obvious how you do the comparison. The true tree is rooted, the inferred tree is not rooted, and you compare them both in terms of being unrooted. And so you can mark the edges about whether or not they are correct or incorrect. And the correct edges are the ones that infer splits that occur in both trees, and the ones that are incorrect are the ones that define splits in their tree but not in the other. So for example, this one that's marked FP splits S3 and S5 from S1, S2, S4, and that's not present in the true tree. So that's a false positive. So that's the usual way of measuring error. False positive rates, false negative rates, or the average of the two. Now, in linguistics, a little bit more complicated because you want to be able to incorporate the borrowing, right? So if you're going to do a simulation so that you actually represent borrowing, you actually have to talk about how does a character evolve when there's borrowing. So here is an example of, again, an explicit network, and each character is going to evolve down the tree, down this network by picking the edges on which it evolves. So it'll evolve down some tree contained inside the network. So that's the way we do this. We have a network, we have the trees contained inside the network, and each character is evolving down some tree contained inside the network. So that's the representation, and that's the explicit relationship. Now, the useful terms homoplasy. So this is, for example, a binary character that's evolving with or without homoplasy in each of these cases. This one, there is no homoplasy because there's only one change, 0 to 1, and it happens here. Here, 0 goes to 1, and then goes back to 0. So that's a back mutation. And here you have 0 to 1 here, and 0 to 1 here. So that's parallel evolution. So you have homoplasy is one of those two events. It's either a back mutation or it's parallel evolution. Another lexical clock is another useful terminology. So when when the branch lengths represent how much change has occurred or the expected number of changes for each site, then lexical clock means that there's the same distance from the root to each leaf. This is no lexical clock, and the deviation from the lexical clock is something that you may want to vary. So it's just like in biology where you have a molecular clock and this is the lexical clock. And the same controversies in linguistics as in biology about whether or not it's an acceptable assumption. Heterotachy, which is the departure, for us, it's the departure from the rates across sites assumption. So this is getting towards the no common mechanism model of Tuffley and Steele. If you have one character that evolves like this and another character that evolves like that, then each is not just a scaled up or down version of the other. You know, with the rates across sites, the differences between the characters are just that some are slower and some are faster. Here, the relative rates on the edges change according to the character. So this edge is shorter than this edge, but here it's the reverse. This one is longer than that one, okay? So the relative rates can be different. So that's what we're calling heterotachy, but it's really the departure from the rates across sites assumption. So previous simulations in this area had been done, and they had mostly assumed no homoplasy and no borrowing. So, and in fact, a lot of them had actually assumed a lexical clock. So, and then all they've done is vary the rates for the characters. Some were slower and some were faster. Now, why did they assume no homoplasy, and why did they assume no borrowing, and why did they assume the lexical clock? Well, lexical clock is just, in some sense, the easiest thing to simulate under, but it's not, doesn't mean that the community thought it was right. On the other hand, there is actually a relatively low amount of homoplasy in linguistic data. And by relatively low, I mean things like if you looked at the rescaled consistency index, you find numbers like, 0.95. So they're very, very low homoplasy, astonishing low compared to biological data. So evolving without any homoplasy actually matched what linguists thought should be true if they could detect all the borrowing. Now, evolving without borrowing is just because it was harder to do a simulation that involved borrowing. Some of the more recent simulations have involved some borrowing, but have still been done without any homoplasy. And the borrowing that they've done has basically been on small networks, that is to say, something like, maybe 6 or 10 leaf networks with one contact event. And then you just vary the amounts of characters that are using that contact edge. So that's basically, previous simulations have been rather limited. So what we did is we did a rather extensive simulation, but this is the model that we worked with. And this was published in Cambridge University Press for a conference that was held at the MacDonald Institute several years back on phylogenies and prehistory of languages. Okay, so basically archaeology and linguistics and biology coming together to try to understand how humans, evolved on this planet. So this model is essentially an extension of Tuffley and Steele's no common mechanism model, but to the infinite number of states situation. So imagine what you have is that each character is going to evolve. A simpler version of this would be the no homoplasy version, so that you have each character evolves completely on its own model, but down the same tree, okay? So if it innovates, it just takes on a new state. That means every time it changes state, you get a new state. So the number of possible states is unbounded, okay? Now, what we did is we allowed this to actually have some homoplasy, because most of the time in linguistic data, there isn't a lot of homoplasy, but where there is homoplasy, you can actually identify it. So there would be an identifiable homoplastic state. And in this first model, we said there's just one homoplastic state. We're going to call it H star. And every other state, is non-homoplastic, and we're going to call it N, or N prime. So on every edge, each character is either going to, innovate or not going to innovate. And if it innovates, it either becomes the homoplastic state, or it becomes a new non-homoplastic state. So you just have to define the probabilities, and these will depend upon the edge and the character. So you have this quintuple. P, the probability that depends upon the edge E and the character C, that you don't change your state. You start at a non-homoplastic state and you stay in the same one, or you go from the non-homoplastic state to a new one, or you go from non-homoplastic to homoplastic, etc. Okay, so you have these quintuples. And now the binary phonological characters, these are presence or absence. The way that they work is that once you have innovated, once you have actually had this innovation in a language, all of the descendant languages, whether or not they still actually have it, will show the vestiges of having it. So you will actually be able to detect that you or one of your ancestors had that innovation. So that means that you can go from, once you're in the homoplastic state, which is the innovative state, because it can happen many times, you have to stay in that innovative state. But you can't go back to the non-homoplastic state, which is the ancestral one. And you're just going to assume that they are always between 0 and 1. All these probabilities are between 0 and 1. And then the other characters have an unbounded number of states, and you just say that the probability that you innovate has to be greater than 0 and less than 1. Okay? So those are the assumptions of how the characters are going to evolve. And you have to note that there is no connection between the characters other than that they evolve down a tree, the same tree, and that you can determine for each character what the homoplastic state is. Now, borrowing we model in the following way. The contact edges have actual sort of, probabilities of transmitting characters on them, period. So that has to do with, they are a contact event. There's a certain strength to that contact event, what's going on there. But then each character has a relative probability of being borrowed. So you have these products, the relative probability of being borrowed for the character C, and the probability of transmitting anything on that edge E. And the edges have different probabilities in the two directions, representing the different sort of sociological forces going on. Okay, so you have this underlying network, and the network contains a tree and these contact edges. The contact edges have these probabilities of transmitting things on them. The characters have their sort of relative probabilities of being borrowed. But other than that, every character has its own mechanism going on. Yeah?
Would it make quite a big difference where the contact edges are, whether they're quite near the leaves or quite deep in the tree? Did you study that, or you just had some fixed edges that you put
In our simulation,
Yeah.
they were random.
Okay.
Not entirely random. There was a probability of having them, which were more likely to happen when they were close together. But nevertheless, we didn't specifically look at the consequences of placing them in different places. So the theoretical results. The first thing is that the model tree is identifiable, and you can identify it using just the splits. Now, the splits you would be looking at for each character, you would look at those characters for which they don't exhibit any homoplastic states. So they only exhibit non-homoplastic states, and they only exhibit 2. So if they exhibit exactly 2 states and both are non-homoplastic, then they define the split that has to exist in the tree. So you can collect all of those characters, and that defines the tree. You could use more of the data by taking every character and looking at the quartets that it induces that go A, B versus C, D, where A and B share a non-homoplastic state and C and D share a different non-homoplastic state. And that allows you to use more of the characters. And in fact, you can extend a result by Moselle and Steele, which was for the homoplasy-free model, and show that you can identify these trees from a logarithmic number of characters. So these results apply to the morphological and the lexical characters, which have an unbounded number of states. And in particular, they have, they allow 2 or more homoplasy-free states. In the phonological character case, you have only 2 states, and one of them is homoplastic, so that you don't get identifiability using these results from the phonological characters. But for those, you can actually get them from a distance method. So you can define a distance on the basis of the binary characters that include some homoplasy, and on the basis of that, you can get identifiability. Yeah?
When you say characters that include homoplasy, is that characters where it's obvious there's homoplasy, or are you assuming you know the homoplasy?
You always know the homoplastic state. So all of these assumptions are with the assumption that you know that there's one homoplastic state and you know it. Though of course you could have any number of homoplastic states as long as you knew them, and as long as you could get to the non-homoplastic states. Now, statistically consistent methods exist, a variety of them, and with sequence length requirements that vary from logarithmic to worse. But you can reconstruct the trees using all of the different kinds of data. With the phonological characters, though, you need an abundance of them because you have to have replication to be able to do it. Okay, finally, it's interesting, but you can compute the likelihood of the tree in linear time. So you can compute, if you're given a model tree with all the values of the parameters for each character, you can compute the probability of the patterns in linear time. So this is not the usual kind of dynamic programming algorithm when you have a finite number of states and it's, you have R states, so you have like an R squared times N algorithm. You have an infinite number of states here, so it's somewhat more subtle. But there's a nice, simple dynamic programming algorithm that you can do to get the likelihood. So, the simulation study. We implemented this model on phylogenetic networks. We only looked at 30 leaf trees, and we added contact edges to these trees. And the reason we only looked at we actually have extended this to larger sets more recently, but I'm just showing you the 30 leaf one. This actually has to do with the problem of running POP. POP only allows a certain number of character states, and if you have data that has too many character states, you can't use it. So it's actually a software problem that has to do with what people thought they were going to have to use. Mark Helder could probably fix this for us, but anyway. So we have networks with 30 leaves and up to 3 contact edges. We had 2 different kinds of characters, lexical and morphological. We used 2 different rates for homoplasy, several different rates of evolution, so scaling the tree up and down. Borrowing these rates were estimated on the basis of the Indo-European data, both for the screened and the unscreened data, so a relatively low homoplasy level and a much higher homoplasy level. And we compared the estimated trees we got to the genetic tree contained inside the network. So you remember the network has a tree in it, and then you have contact edges on top of it. So we're looking at what happens when you are analyzing data that has evolved with burrowing and with homoplasy, and you're reconstructing a tree, which is why we didn't look at the methods that reconstruct networks. We were just looking at methods that reconstructed trees. What happens to those estimates of the genetic tree? How far off are they? So the data doesn't evolve under a tree, but you're estimating a tree. How bad are your estimates? So the observations, and then I'll show you data. First of all, the choice of the reconstruction method does make a difference. It's not like all methods have the same level of accuracy and just differ about what kinds of errors they make. The relative performance between the methods is in fact quite stable, which was surprising. It may not remain stable when we go to much more complicated things, but we have roughly doubled the size of the number of taxa and doubled the number of contact events, and we still see the same relative performance. So it may be stable in a wide range of model conditions. And in general, the distance-based methods do worse than the character-based methods, which is not surprising. That's a pretty standard observation also in biology. The choice of data matters. It has an impact. And what we mean by that is that our morphological characters are by design for the simulation more resistant to burrowing and more resistant to homoplasy. And when you have more characters of that sort, it does tend to improve the reconstruction, not for all methods, but for most. Accuracy, surprisingly, is only slightly lessened by increases, small increases in homoplasy, burrowing, or deviation from a clock. And then the most interesting thing, but maybe obvious to everyone, is that heterotachy, which is to say deviating from the rates across sites, improves accuracy. You know, having seen it, it sort of makes sense. Edges that are small in one character will not be small in another character. But you could do that with the rates across sites and just have fast evolving rates and slow evolving rates. But then to get the short edges longer, everything gets longer, so you get more sort of overall noise. So heterotachy, in a sense, is a way of getting edges to become visible without adding too much noise. It's weird. But anyway, I'll show you the data. So this is an experiment, moderate homoplasy, and what we're looking at, since it's moderate homoplasy, we are not looking at the weighted compatibility method. We're just looking at 4 methods, which is to say UPGMA, neighbor joining, Gray and Atkinson, and maximum parsimony. So UPGMA and neighbor joining are both distance methods, and these two are both basically sequence-based methods. And this is a condition where we're looking at the deviation from the clock. So a small deviation from a clock to a moderate deviation from a clock. And what you can see is that the relative performance is the same for all of those, okay? And this is, here is the topological error rates. This is 10%, that's 15. So you can see that the relative performance is the same, but you know, UPGMA is affected more seriously. Here we're looking at the variation of heterotachy from small to larger. And again, the relative performance is the same. Varying the number of contact edges from 0 up to 3, and the relative performance is the same. So as we vary these parameters, the relative performance is staying the same. Now this is the low homoplasy condition as opposed to the moderate homoplasy condition. So because it's low homoplasy, we do look at the weighted maximum compatibility. So now we have weighted maximum parsimony and weighted maximum compatibility. We have 5 methods here. Again, deviating from a clock, from a small deviation to a large. The relative performance is now the same, and we've added the parsimony and compatibility methods, and they're actually basically outperforming very slightly Gray and Atkinson here. Varying the heterotachy, the same relative performance from left to right. Varying the number of contact edges, same relative performance from left to right. Now we're just looking at varying the homoplasy from moderate to low. So you go from moderate to low for each method, very little difference in performance, very little difference in performance. There's a slight improvement here, but it's really not statistically significant. There's a little bit more improvement here, but you know, the error bars are overlapping. So you know, there's not much improvement obtained by reducing the homoplasy, which is interesting. This is the same thing but on a tree. The previous one was on a network. This is on a tree. And it's the same sort of story, very little improvement by reducing the homoplasy. Or another way of saying is very little increased error by increasing homoplasy. Increasing the number of contact edges, this is an interesting thing. You go from 0 to 3, UPGMA gets slightly better. Granted, the error bars are overlapping, but why is it getting better? I mean, you can sort of imagine, since it needs things to be, you need to have some sort of connection to time. Contact events can only happen at the same unit point in time. Maybe this is some way of connecting things to time more. I don't know. Neighbor joining gets worse. Gray-Atkinson, it's a little bit unclear. Maximum parsimony. You know, it's interesting. With one contact event, both of these methods are slightly better. But weighted maximum parsimony, weighted maximum compatibility gets slightly worse, but hardly any impact from adding contact events. Same story, but a slightly different situation. We're looking at networks now. But it's the same kind of story, just not much impact except, this is the deviation from a clock. You can see that all these methods are slightly worsened by deviating from a clock, but it's really slight, whereas UPGMA is very much worsened by deviating from a clock. But interesting robustness. Impact of heterotachy. As I said, increasing heterotachy is improving things. It's very marked. It's a really big improvement. It'd be nice to see a study like this in biology. I mean, we could do a DNA sequence simulation and deviate from heterotachy by going towards a no common mechanism model, see what happens. Maybe things get better, even though it violates all the model assumptions. Big improvements in accuracy as you go from a small amount of heterotachy to a larger amount. So I think this is one of the more interesting observations. Now, the impact of data selection. This is a question about what happens as you go from 361 characters, of which 360 are lexical. Then you throw out some of the lexical characters. Now you only have 300 characters. And then you start adding back in morphology until you're finally up to 360 characters again, but now 60 of them more morphological, so i.e. higher quality. And what's interesting is that, as you expect, the difference between the first two is a slight increase in error because you're throwing out data. Right? You start off with 361 characters, you only have 300 characters. But then you have improvements, right? The error rates go down, though not here, and not really here, and not really here very much. But you can actually, if you have a method that really looks at the high quality data and weights it highly, you can get a lot more signal out of it. So these were the observations. Again, the choice of reconstruction method does seem to matter. The relative performance does seem to be quite stable. The differences are not necessarily big, but under some conditions, the differences are substantial. The choice of data matters, but again, it only really has an impact if your method can figure out which data are reliable and will weight those data more heavily. And accuracy is only slightly lessened with small increases in these generally considered unfavorable things like homoplasy and borrowing and deviation from a clock. But interestingly, deviating from the rates across sites model is improving things. That again is for me one of the interesting ones. We do need better models. It would be good really to have methods that are based upon stochastic models that actually are based upon good models of language evolution. And there's a very interesting question that has come up about how to model language evolution, in particular just what are the characters. You know, if you have the single word that represents a given meaning, you have monomorphic characters. But you have to look at how semantic shift is impacting and defining homoplasy here. And if you allow multiple words for the same meaning, then you have to actually broaden the definition because the meanings are not actually all that close initially. And semantic shift is actually happening all over the time. So it's a funny kind of situation that really goes at the heart of what is it that we're actually modeling, not just how does how do we model it, but what is it that we're modeling? What are the characters? We have not really studied the impact of screening. I mean, the simulation doesn't really say we're simulating evolution, then we're throwing out data and we see what happens. We're actually simulating evolution under different conditions and looking what happens when you look at data of different types. It's not really studying the effect of screening, and it would be very interesting to look at. And how do we detect and reconstruct burrowing? This study did not look at methods that are trying to detect burrowing, reconstruct graphical models of burrowing. It was just saying, what happens if we reconstruct trees from data that have evolved with burrowing? How much impact does it have? And so far it says it doesn't have a huge impact, but it would be nice to see if the amount of error that is present we could reduce by actually reconstructing networks that were explicitly reconstructing that history. How do we handle missing data? That happens a lot in linguistic data. There's a lot of situations where you don't have the words for some meaning in some anciently attested language. You just don't. So what do you do with all that missing data? How do you model it so that it reflects properly the stochastic process? And how do we handle polymorphism? Because polymorphism happens a lot, and we really don't know how to correctly model it. There's a lot of ways in which you can end up with more than one word for a given meaning. You can end up with it from borrowing. You can end up from semantic shift. You can, all sorts of things can lead to polymorphism, and modeling that appropriately is still something we don't know how to do. And there's a web page that has the data and the papers that's maintained by Louis Nekle, who is my former student. Thank you.
So I'm a bit worried about the word, or what you mentioned, the whole idea of a stochastic process. So biology and languages, they're both like historic things. And so in biology, when we talk about evolution, we kind of hope that there's been so much time, so many generations, billions of years, and so on average, things that are going to be statistical, because even if there are some big events, over time they average out. But now the languages, I mean, historic events that just happen for some reason. Some people get conquered and their language gets completely wiped out or modified. All that, is that all going to average out and be treatable in a statistical way, or is it?
Well, it's a very good question, and I guess I would say that I think that's one of the reasons why trying to do a stochastic model where you're assuming that your data are evolving, like different characters are evolving under the same process, it's less likely. You know, because you don't have the kind of time to average things out, and you don't have the amount of data to average things out. Whereas situations where you can hope that whether it's stochastic or not, there's signal there that you can somehow use. It would be nice to model it stochastically. It would be nice to have a statistical model for this. But yes, to some extent, I agree with you. It's not clear that a statistical model is going to work, but it would be nice to try. And it's a good question whether or not it will work. I don't know. It's clear that because of human life, you know, that these things are not simple. They don't have the same sort of random kind of stuff that's happening on them.
Yeah, so when we analyze fossils and biological data, we just treat them as other leaves in the tree. But in this case, it seems like you might be able to say that Old German, for instance, is a direct ancestor or an ancestor of modern German. So maybe have you thought about working with methods that, or developing methods that have nodes of degree 2 in there, and just put some of the old languages?
What we actually have done is not use the more modern stuff. So what happens, let me just go back to the picture in the beginning. What happens, this time depths for the leaves are actually from the attested dates for when the data were gathered. But for the ancestors, it's just estimated. But Greek is a lot older than, the Greek data is a lot older than Germanic data. And sure, we could have taken modern Greek as well, but the inclusion of modern Greek would not have helped, because basically it just, you know, you might try to get what happens inside here, but two things. One is that the modern languages just keep there's so much turnover. Turnover is fast enough that you basically lose signal. And secondly, once you look within these groups, you really get population level effects. So in fact, it does look more like a dialect continuum. So there's two issues there. One is using the more modern stuff means you've lost. For example, where's Albanian? Here. Albanian's lost just about everything. So that's why it floats. Things that have lost their morphology just tend to float around. So the more modern stuff you use, the harder it is to place it. It's just like the usual rogue taxon problem. And then you also have to deal with the fact that you're dealing with population level processes, and you really aren't going to get anything close to a tree at that level. So those are the two issues. But there's nothing about most of these methods that couldn't, in fact, otherwise just take the data and interpret stuff with internal nodes. I mean, all of these methods could interpret things as being at the internal nodes just by collapsing the edges that go to them, right? So that would not be an issue. The issue is more the loss of data. Yes?
When you said, we talked of more or less heterotachy, do you mean more or less sites showing heterotachy, or did you mean more extreme rate differences? I didn't know what you meant.
Well, I explicitly did not mean rate differences. I mean rate differences, but I mean rate differences towards the no common mechanism model. So the kinds of, what we're actually doing here is we're starting off with, so this is not, I wouldn't call this a rate difference. I would call
I mean, in terms of the edge lengths of like the pendants there, I mean, the ratio, so you've got a short one leading to A and a long one leading to A, they could be more or less longer or shorter. I didn't know whether you meant more sites showing this behavior or...
Oh, okay. So in the simulation what we did
Yeah.
is we started off with an underlying tree, which we generated in a random process. Start with a birth death tree, then deviate from a clock, right? Then we have this underlying tree. And then we added some noise for each edge and for each character. So that noise, if there was very little noise added, in fact, if there's no noise added, then all the characters have exactly the same rate. And otherwise, what they have is some of them are going to be, the relative proportions are going to change. And the amount of noise you add changes how much that can change. So when there's very, very little of that, then it's a very small deviation from this kind of situation. But all of the sites are evolving with this kind of just added noise. The question is, how much added noise are they evolving with? Yeah.
Generate the noise?
How do we, well, it just, oh God. The details are
you can tell me
in
them
here,
individually.
but it's basically, you know, you have a particular edge length, right, for the underlying tree. Then you're looking at a particular character and you're flipping a random coin with a certain expected value, and then you just add you multiply that edge by 1 plus the number that you created. So that number could be 0, right? If you have no noise, then you multiply it by 1 and you get back the same edge. And if you have a lot of noise, you might multiply it by 1.3 or something like that. So it's this kind of deal. But that's as close as I can get to you without going back to the paper and saying, okay, what exactly did we do? Yeah.
Any further questions? Doesn't seem to be the case, then please join me in thanking Tandy